Welcome to this session. So let's get started. This is really about if you have been implementing something recently. I think our experiences on how we took on Cassandra and staged it for how we can change things in Cisco Commerce, and I'll briefly explain what Cisco Commerce is. And it's been largely the last 1 to 1.5 years of learning and re-architecture that we've been doing on this platform. I am Hatinder Chawla. I'm responsible for architecture and engineering of the Cisco Commerce platform, and specifically of a renewals piece within that platform. So what is Cisco Commerce? Cisco sells networking gear, routers, switches, a lot of IoE devices now all over the world globally. At Cisco Commerce, we enable that sales. We make sure that our partners and customers who want to transact with Cisco are able to come and buy from us. Buy means all channels that we offer. The web channel, which is a very predominant channel, the B2B channels, which are direct business-to-business integrations, and the mobile channel, which is more up and coming and provides certain part of the capabilities, but not the whole set today. So when you look at Cisco, $50 billion in revenues, the way the revenues come in is through the Commerce Gateway, and the front-end application is what we manage here. So what's so special about our use case? Well, part of commerce and part of transacting in Cisco is what we call the renewals. We have devices that are sold over years, over months, and what happens is you build an install base. And we also sell service contracts on top of that install base. We sell subscription contracts. They're up for renewals, and they come together. So what that does is sometimes these are really small quotes that we create, and after the quotes, there are orders. But especially with the case of renewals and contracts, the size becomes very huge. And by huge, I mean it's really thousands and thousands of items within that. And each of those items can have another tens, dozens, sometimes 100 items within, sub-items within that. So it's a complex configuration. And what happens is, because of the large size, it's no ordinary small quote. It's just almost becomes from a transactional problem to a big data problem. And then what we do is we take all that, run it through a lot of business rules to make sure that what we sell is something we can actually commit to and is valid. So that causes a lot of operations as well. And then there is variability. It's not a steady state stream. There are times when the usage is low, and then there are times when the usage is high. It depends on business cycles. So it's not like the consumer world. It depends on business cycles, and business cycles change quite a bit. So we accommodate for peak usage times, which are very different than our low usage times, and multiple factors over. So what we wanted is, as we look at our problem and re-architect the systems, it should scale linearly. And we should be able to add more as we expand business, and it should not degrade performance for us. Plus, handle a lot of these large quotes with a smaller time span, and customers don't have to wait on our website with a spinning icon. The other thing is just zero downtime. Just like any other commerce application, it's important that we stay up 24/7. Today we don't, and as we're upgrading, we're getting to that. So that includes for our deployments and code changes, as well as for the technology upgrades that we do. Now, it's important to know that the Cassandra piece is a part of the puzzle. The overall puzzle is much bigger, and zero downtime as a target that we try to get down to is for the overall architecture that we have. Low latency is important from anybody trying to come and transact and do business. You don't want to be waiting for a long time. So it's not just scaling, but scaling at a way where we can provide low latency to our customers and partners. The other thing is, as we go into the cloud world, we wanted to use a set of technologies that have the elasticity to scale up and be able to use a lot of the capabilities that are available now to add more nodes more automatically than to use older IT processes to expand your infrastructure. So sort of like on-demand scaling with elasticity, and use a cloud model for their architecture. This is another thing where everything we're building now is API-based, and the web front end just serves from the same API as the B2B will serve from the same APIs. So just building an API interface on top of all of that. So what does the overall architecture look like? These are just some of the big components that we use. We have if you look at the bottom, we have a full enterprise services suite. Now ERPs, everything is there. We don't expose that directly in our front-end e-commerce, but we do have business logic and rules running there, and a lot of data comes out of there. So we have that bottom layer, which is our back office there for us, and it also provides a number of other services. What we do then is we have a top layer of services. That's where we build all our APIs, and this is typically Java for us. We have standardized on that. We may expand to more languages, but we predominantly are running on Java, and for that we use a Tomcat server. This is not a single server. We run multiple servers, and depends on how we divide and subdivide the business logic. We have at least 6 to 7 different services, and they all have a number of horizontal scaling capabilities. The middle layer is some of the more important ones that I wanted to talk through. It represents our data layer to a large extent. We do, for things we don't need to store, we do use Memcached. For the data store, we are going with Cassandra. For search engine, we use Elasticsearch. And then we actually enable a lot of the logging and the information and channel it all through the Elastic Search, Logstash, Kibana stack, ELK. So we get intelligence on the data that we are building. One thing is that this has been relatively new for us. So this is something that we've been working on for the past 1 year. We are in production. Now. But a lot of the learnings have come from non-production activities for us. As we expand and get revenue out of these engines, we'll go and learn more of this and change according to that. So when we went through the re-architecture, actually, we did not just straight away land with Cassandra. We went through a number of revisions and versions of how to do it right. And the first one was just get a better relational database model to do all these activities, which means just have the right primary key, foreign key relationships. Don't add too many indexes. Don't slow down your inserts because you're optimizing too much for certain reads, and then you just get to pay a penalty on the writes. So try to run a simplified relational data model, and then after that, as we ran load tests, we wanted to get better. We partitioned the data by the data set by dates, and that helped a little. And then we were still not very happy with the reads on the data. So at that time, we brought in Memcached, and that gave it a typical Memcached front-ending a relational database architecture, where for reads you're able to get to Memcached. But at that point, we could have gone with that. It was pretty good, but there's this whole NoSQL world. And we really wanted to test the waters of, is there something better than this, or is that going to be the end? At that point, we did some NoSQL testing and benchmarking, and benchmarking our own application against a NoSQL database. And at the same time, along with the other relational and Memcached version that we had. So we did make a choice to switch over, obviously, and based on how we were able to get a lower latency operation on the NoSQL database. Then finally, we didn't remove Memcached yet, but after we got all the numbers in and just saw from Cassandra perspective, for all the writes and reads we were doing in Cassandra, we didn't find a need anymore to maintain our Memcached layer, so we just, at that time, just knocked it out. So that's how we end with a single Cassandra database. So how did we get to Cassandra and not any other database? Well, we did start with, these are probably the core competitive ones that a lot of others look at as well, right? So we had HBase, and then we had a strong reason to go with HBase because we have a lot of Hadoop work going on, and we do support Hadoop already. So HBase is an incremental addition to that. It's a simpler choice to make. Cassandra was there because it was just, at least on benchmarks, it was just sort of beating the crap out of every other database. So definitely wanted to look at that. And MongoDB as well, and especially MongoDB because we were already handling JSON data. All our API interchange is now standardized on JSON. We moved out of XML, and our APIs are REST APIs and JSON data sets. So it made a lot of sense for us to see in a database that would actually more natively support it and allow capabilities for searching and querying on JSON data sets. But ultimately, the criteria was one where, first and foremost, we wanted to make sure that we actually built something that provides for low latency. The other one is we really wanted this to be able to scale to the thousands of items that we have to manage in the single quote. The other thing was we didn't achieve active so far. We have run active-passive on our data centers. And this was also an opportunity for us to go to active-active because in the future, what we look at is if you look at commerce, it's not a single place from the globe where you want to transact, and possibly we'll look at expansion outside of our US data centers and run from, say, a European data center or somewhere in Asia Pacific. And then the whole reliability of using a single master model or peer model. From this analysis, we kind of took MongoDB out early on by just reading and looking at the published tests on that. HBase and Cassandra were pretty close, and especially because HBase was closer to the Hadoop installations that we have. We did performance tests and benchmarking on these, and Cassandra was just coming out better. Plus, on the benchmarks we performed, and this was in addition to the published benchmarks that you can see on some websites. Plus, there were really other reasons, which was the active-active vision where we wanted to go was also a strong reason why we would finally go with Cassandra. So that's how we decided on the NoSQL option. Now, how do we design this? So the data model, if you really look at a large part of the commerce interaction is all about creating a quote. Now the quote has a lot of complexity in it. It has items, and those can vary depending on what you want to purchase, but it goes from tens to thousands. The items have actually, believe it or not, lots of attributes to them, and over 100, and it depends on the business model how many there really are. And then there are errors and corrections we manage within that space, and also an item can have sub-items. So when I talk about items and sub-items, you're really talking about a box, and the box can have a board, and the board can have memories and power adapters, all of that. So it's the full configuration we're talking about here. Now that's a huge data set that we had to manage. The other part was our code base was already interacting with JSON as the model for interaction between two services. And the other point was that our Java code already had our Java objects embedded, and we had a way to get our Java objects to work with our JSON objects. So, and then there was another criteria which was important, is we were really never sure. Honestly, until we really get a couple of years in production, we will probably not be very sure either. But we wanted a way where we're not too much into the details or capabilities that Cassandra offers, and they're not available from other NoSQL databases. So kind of keeping your options open for an easier migration if we have to move out of Cassandra again. The data model we chose is we really partition by the quote identifier. We use actually a JSON data format. So instead of creating a lot of columns and column values, we store a lot of attributes in a JSON. that we're getting as a standard part of our API interaction and store that whole JSON data set. And we reverse that. So this also helps us connect from our Java object stack into the JSON, and from the JSON to the database, to the data stored in the database as well. Now, if you really wanted to, there are other databases where it's also easy to store if it is stored as a key value pair, and that's what JSON implies here for us. Then there are a few column families. We don't have too many, but there are a few column families depending on the relationships between them. Like we kept the errors separate and the items separate, and then there are majors and minor relationships. We kept them separate. We kept some code header level information separate, but we then separated out into a few column families instead of saying, hey, we'll just use one column family. So it also has to do with the amount of updates and changes that go and on each one of those. And I'll just talk through a few things that we went through as designing and implementing. One of the big problems that you just get into is suddenly you don't have a sequence. Relational databases, you could get a pretty sequence, and just every time you count it up, it goes by one, and it's very reliable. So we had to figure out a sequence, and UUID was not going to be the pretty sequence that we will expose out to our partners and customers. Plus, people talk about it, and they talk over telephone, and they give each other numbers. So it becomes, it's not a usable primary key for us. We tried a user ID plus counter mechanism first, now only to find that the counter as well is not very reliable, although we use the user ID as a means to say, well, for a user, maybe the counter is going to be reliable if it's not a global counter now. But we had issues, and especially when a node goes down and bring it back up, the count, you would actually get two quotes with the same code ID, and they would overwrite each other. So then we replaced that with a counter plus milliseconds to just make it more specific and add like a few digits of the milliseconds since elapsed time. Now we're still evaluating how we evolve this further, but we're trying to avoid going to a single master to get a sequence and keep it more of a distributed system and a reliable way where we can get our primary keys also in a high availability fashion. But ideally where we're trying to go to is just have a number-based one and then still be reliable in a distributed system. On the code, we split it out by taking our Cassandra operations out. We didn't do that immediately, but soon we saw that the code was just getting a little bit infested with this. And it also didn't work out with our plans if eventually we want to remove or change our technology. We wanted to abstract that. So we built an abstraction layer on all of our persistence data, which is essentially ended up being Cassandra, and separated it out so that it's not to one individual team, and we have a larger team that actually builds on the whole platform and multiple services, so that the persistence interactions are modeled through that abstraction layer. And within that abstraction layer, we keep certain key principles that help us with making sure that we're not too intertwined at deeper levels, and we're making the right architectural decisions. Then we use the Java native driver, SQL 3. We started off with the S10X driver up front, but then changed to the Java native driver after not too long on the S10X drivers. Consistency levels, that is another key design thing that you encounter. So should it be quorum? Should it be one in some cases? And how do you balance between consistency and availability? So what we did was definitely chose write to be on a majority basis and choose one local quorum for all our writes. When it comes to reads, we have actually split it between, in some cases where we do a read of one, and in some cases where we are doing a local quorum. And we're still going to finalize where it ends up being, because ultimately the price that you pay is based on if you are doing a read quorum as well, then you just have more nodes that are processing your data set. And if you're really having a lot of high throughput needs, then it does slow things down. And especially in a case where we were loading data and upfront loads they cause a lot of load generation. We have constant writes for 24 hours, and that whole, and then we read it out of there, and that would just proportionately depend. If you just add one more read, it proportionately just decreases your read time. So we balance it out between the core, between trying to be consistent and trying to be fast in the nodes that we have. When it comes to the core quote data, we want to be more consistent, and that's where we are using the local quorum. And when it comes to some other data, we choose one. On an infrastructure basis, we have actually, we are using an OpenStack internal cloud. This is, we have an API-based integration with our cloud, so we can get nodes provisioned through our APIs. And we have not gone to a local attached storage model yet, partly because that's not a standard offering yet in our internal cloud. The other one is we're still debating internally between making that a standard offering or just using a shared storage model. We do use a shared storage model. Now, it is, it's known like you will be slower in that. I did a comparison between SSDs and the shared storage model that we have. So the SSD was certainly faster and would get more I/O. Throughput as well, 50% more. It wasn't like multiple times over. The latency was a little bit better, not too better on our SSDs, and I think primarily we attribute to, we use a lot of networking gear, and on the back end we had striped the data in our shared database model quite a bit, so we got the performance that we wanted. So just based on performance, we're not going to make a decision alone to move to local direct attached storage. It will be based on factors for how do you handle failures, and do you have a, kind of like, if one, can you cause a more catastrophic incident if you have a problem in your storage layer itself? So it's more about the failure than about the performance right now in our mind as we move towards that. The low latency actually we will get is through the memory. So any operations that you can get through memory is much better, and a lot of our data set is actually hot for us. So people use it. The quotes are very active. There's a very active usage of certain data set, and then it just dies down because it's not needed anymore. So we do depend on hot caching. We do, at this point, we got 64 gigabyte machines, out of which 50 would be used by file caching, OS level. So we are able to leverage that quite a bit, and that's where we get most of the performance improvement we have, so we can scale more horizontally on that. And at an infrastructure level as well, we are backing up to a NAS system, which is part of our standard infrastructure offering. On compactions, we have actually started off with size tiered, and then we had a lot of updates and heavy update scenarios with our quoting capabilities. So we said, hey, let's go to level tiered. The other issue with size tiered was we needed much more storage because you need double the storage to run compactions through when you use size tiered compaction strategy. So we're trying to go towards, hey, use level tiered compaction strategy, especially from quotes where we have a lot of updates. You get better read performance because the number of SS tables should be lower. One of the problems we had, though, is when we moved to level tiered strategy and we did the big bulk write loads, and this we knew after the fact, we really had compactions running for hours and hours. And when I thought slow compactions, I really thought we'll catch up in a few minutes. But this sort of surprised me as well. So we started looking at the compaction strategies more seriously, and the pros and cons against use of additional storage versus actually being able to run your compactions in a reasonable amount of time. So for the larger loads where we had a lot of write operations, we moved back to the size tier compaction strategy. And just changing within, while everything is running is fine as well, we tried that in practice. You just want to make sure you have enough storage. Well, so these are kind of the tools we use in addition, just to make sure our monitoring is in place. We have all the rest of our architecture monitored through Nagios, and then we also have Ops Center from DataStax. So these are core to Cassandra. In addition, we use certain Linux commands. These are pretty much all we use, or I use. Some people may use more or less, but that gets a lot of additional information that you really need to know what's happening here. Is it my disk that's having a problem right now? Am I getting the right throughput? Should I tune certain parameters? So you get a lot of good information through these Linux commands. Node tool is absolutely brilliant. Just use it. There are many commands you can use it there, but just the stats on the column families and compactions and the transaction processing stats, they really let you know what's really going on in the system. And several times you really were wondering, okay, what's happening? How long will the compaction last? How much more is there? So we could use some of the TP stats numbers to determine that. Additionally, Cassandra stress, that's important. As we were especially going through a lot of POCs and trial and really knowing what is good, what will work, what is this, and we were setting up new environments. Are the newer environments also scaling to what our original plans were? We use Cassandra stress quite a bit there as well. We used both the versions. The older version is pretty good. The newer version is also there. It's got a lot of more features. And then we use performance benchmarking within our tools, where we actually run daily numbers and snap those numbers about 4 times a day and just see, because we have a lot of active code-based development and anything can slow down our numbers. So we do a lot of active benchmarking and multiple times a day that we keep our numbers coming. And if we see slowdown, we really know at what point it happened. So we're able to trace back to it. Storage, this actually has been like whenever we thought we got it right, we really didn't get it right because it just is a complex formula to figure out how much storage do you need. When it was with relational databases, it was a little easier to manage and you could predict. But there are many factors that contribute. I mean, the easiest ones are the kind of, you start off with multiply by the number of replicas and then by the compression that you're getting. So that's your basic. And then based on the compaction strategy, you allocate additional storage, right? Size tiered, you would want to be double so that you can actually compact everything and not go out of storage. Sometimes we do node removes, and this happened to us as well. We had a node go bad, and then we did a node remove and didn't pay much attention that when you do a node remove, the replicas will move off to the other ones and impact the storage capacity planning on the other nodes. So you need to think about that as well. Snapshots, truncate tables, delete tables. It happens a lot in our more in our development and staging environments and testing than in production. But that data stays, and you have to manage that through as well. Either just turn it off, or if you keep it on, have some sort of a program that'll remove it and keep allocations for that. Then the data balance isn't that perfect. Actually, we see quite a bit of variation between our nodes, and it's enough to tell that you need to think about your storage, just not on the perfect distribution basis between nodes. Repairs cause some storage increase. And then there are just some special scenarios which we never could figure out why it happened, but it just happens. Like every node would run fine, and this one node had like 280 gigabyte of data, but the total data size was 480 gigabytes, and it was hitting very close to our limits. And ultimately, it is our 100% storage consumption, so we had to expand that storage and let it run through its compactions, and then it came back again. So some weird stuff can happen which we cannot explain, but storage sizing has been one of those where we have been taking steps at a time and learning through that. Then a few things we separate clusters by a few core environments, but then within those core, we actually use key spaces. Developers can have key spaces if they need to. They're in a separate branch of development, or for some other reason, but we don't try to create too many Cassandra clusters. Things that we are evaluating still, and we are still working on that, is operational reporting, how to get that going on top of our data sets, because that's key. Then multi-data center. We want it to be active. We have not gone active yet, and we're looking at that as well. and then expand into multi-region data centers as well. So that's all that I had. I would open up for any Q&A at this point. Yeah.
What are the main kind of business use cases for your kind of Cassandra? So did you kind of fully replace your relation database?
So we are working on the renewals use case, and that's specifically for where we have a large quote sizes and large volumes of data that we deal with. Those we're replacing, or that's where we are actually using Cassandra. We also have other use cases which work fine and don't have the same problems. We're not changing those. At least there's no decision to change those in the short run. Yeah.
You mentioned bringing up more nodes dynamically. How often does that happen and how expensive is it?
The what?
To bring up another node.
It's not too expensive. We actually have done that quite a bit whenever we felt like we needed more storage, and then we were not going to just add storage to existing nodes because there are memory constraints as well. We are able to expand, and it's not a big deal. You just add a node and then bootstrap it and do some cleanup after that on the other nodes of data sets.
So how long would it take?
The whole process? A few hours. Yeah. We typically just get it going and then let it run, and then just comes on.
Last slide that you said that you were currently working for a multi-data center. So does it imply that currently you are with only one data center in your cluster?
This cluster is on one data center, yes. And we're working on plans to expand it to a second data center, which we have for local availability. And then the other one would be to get more across to a different region. But from all settings that we have done, we use the DC-aware settings already on this. So we're close to expanding, I think in March.
Do you plan to use a new collection type persistence? You mentioned that you store JSON key value. Do you expect on that?
The new collection types, we don't intend to use them. Probably later on, once we're comfortable that we are staying here, but at this point, we are keeping with our JSON data formats. And we don't see a whole lot of value yet in that.
Why did you choose Cassandra over database? What was the main sort of reason behind that?
The ability to go to active-active, not have a single master. And then on performance benchmarking, we found that Cassandra was on comparable hardware. Cassandra would give better ops per operations throughput.
Can you talk more about the integration between the ERP? Which ERP are you using? And can you talk about how easy or difficult it was to integrate with Cassandra?
It doesn't matter actually, because we abstract out the Cassandra layer. All our business logic is in our Java layer. So they don't know each other directly. So it wouldn't have mattered to us. But one thing is there that in previous designs, if you had certain capabilities of connecting ERPs directly with relational databases, you cannot do that anymore. So you have to have your business logic somewhere else. Yeah.
Any difficulties concerning the developer side to go from traditional databases to NoSQL?
There is quite a bit of learning. After SQL 3 came out, it became a lot easier. Thrift was sort of a much different area, but there is quite a bit of learning in getting there. And we don't have every developer doing Cassandra work. We have a few, and but SQL 3 makes it better, but you have to retrain through that.
For your case, how much do you estimate the learning curve to move to Cassandra for developers?
A few months in our case. Yeah.
Was there anything caught you by surprise that you weren't expecting from Cassandra as you learned more about it and moved into production?
Things that we were not expecting initially.
Was there any surprises, any glitches?
We've been learning throughout on this. All the compactions has been a learning. Storage sizing was a learning. Initially, we had very simple models for those. Just understanding how the file cache and memory would behave was a learning as well, because we didn't really go in knowing all the details. We certainly did some benchmarking, but after that, a lot of this was learning on how to best get low latency operations, how to manage your storage, how to manage replicas as well. Should it be 3, or in one case we did 2 and then we came back to 3. So we have changed quite a bit through this time period. And we were not experts. We didn't get professional services. We learned on our own and did it.
I'm just wondering if you were using any kind of e-commerce products for your platform, and how did you manage the migration from RDB and happening with NoSQL?
Yeah, we are. It's mostly custom when it comes to the front-end commerce. The back-end has more of the packaged products, but all front-end commerce is custom. And we have business rules engines as well in our setup, but they're all in our services layers. Okay, so can you take one question? Okay, last please.
My question is, how do you stage your app when you create or something like that? How do you manage the push to production?
The path to production? We have a development, test, and then production path. Yes, development, test, and production. And then we have a side path for performance testing. And then once it's in production, we have a production code path as well, from development production for the current release. All right, thank you very much.